Welcome back, everyone. We are going to start the second lecture on entropy and the second law of thermodynamics. I know that the first lecture was a lot. It was really dense with some statistics and probability, and it was probably a lot to comprehend. Hopefully, after we did some of the in-class exercises, it became a little bit more clear. Today, we are going to learn about how entropy was actually discovered. The statistical explanation came later, but understanding heat and the flow of heat and why spontaneous processes happen actually was born from an engineer's desire to build a better steam engine. So we have to review a lot of things before we can dive right into today's lecture. First, I want to talk about what a spontaneous process is, that we covered this last time. We're going to watch a quick video on a spontaneous process, and I want you to reflect about which direction this could go in. Which of the two videos was the real life video? Well, I'm sure that you know that dropping the food coloring into the water and it dissolving is the real life process. Remember last time we had a microscopic reason of why the opposite doesn't occur. Imagine that in the reverse video, all of the red food coloring molecules decided on their own to come back together in one drop and then shoot back up into the bottle. It's not that it would be impossible that that would happen. It's just completely statistically unlikely. We gave the examples of a pool table with pool balls being hit, and once the white cue ball breaks the triangle of cue balls and all the balls are going different directions and different speeds, it would be unlikely that they would all come all back together again. It would be unlikely that they would even all be going the same speed. And that's what this showed here when we talked about the velocities and energies. Once things start all going different speeds or different velocities, it's unlikely they would arrange themselves into groups of speeds that are all the same. And once things spread out in space, their energy levels get closer together. And that's why there's more options for speeds for them to go in. So the food coloring drop that dissolved in the water is an example of this phenomenon. We talked about ways that we can increase the entropy of a system by increasing the number of molecules because there's more energy carriers carrying energy all throughout space. Increasing the temperature increases the total amount of energy and the amount of rungs on the ladder, so different speeds and velocities that they could go in. The volume, once they spread out into a bigger volume, they have energy levels that are closer together on the ladder, so there's different speeds they can go in. And we also talked briefly about molecular complexity, and that's just that bigger complicated molecules can vibrate and spin in different types of directions. We also reviewed the Boltzmann equation, and the important thing is just that we're talking about the ways that molecules can be arranged, both their location in space, their position, and their velocities and momentums and energies. And those total number of ways, because it's such a huge number, we were working in logarithms instead of regular numbers. Also, a while ago, we learned about the gas laws. And remember, the gas laws are really how we began to get an understanding of modern chemistry. And here, three scientists studied phenomenon with gases: Boyle, Gay-Lussac, and Charles. And they found that when you increase or decrease pressure or volume or temperature, one of the other variables is affected as well. And once we combined all of the three laws, we found the ideal gas law, PV equals nRT. So that shows, again, that changing one thing, like changing the pressure, will change the volume or the temperature as well. We also learned that when things, specifically gases, expand, they can do work. Basically, if they're expanding against a force that is opposite the way that they are expanding, They're going to do work to counteract that force. And this is one of the main ways that engines do things for us. For example, in a car, in the cylinders, gases are expanding and raising the cylinders up and down and turning the engine. The formula for this work is usually F delta X in physics. That would be at the top. But when we are talking about a cylinder and gases expanding in volume, we can say that the work is negative the pressure from the surroundings, and this could be atmospheric pressure, even if it's not in a cylinder, or a piston that is on top with weight on it that the gas is lifting up. And that pressure times the change in volume. Now, if the gas is actually contracting and reducing in volume, that means that work is being done on it by the force that is pushing the cylinder down, or by the atmosphere. And if we re-examine the ideal gas law, we see that changes in energy on one side can affect changes in energy on the other side. So when we look at the PV side, we're usually thinking about work with pressure and changes in volume. And if we look at the right side, we're usually talking about heat from changes in temperature. Now that we've reviewed all the background things that we need to know for this unit, let's talk about the can-do, the objectives. By the end of this lecture, I hope that you can say, I can describe how engineers studying steam engines helped form our understanding of energy dispersal. And I can explain entropy and the second law of thermodynamics from a macroscopic point of view. So let's talk about steam engines. The first engines were engines that were used to pump water out of mines, like coal mines or mines where they were digging for different types of minerals or iron or things like that. Those engines from pumping water out of mines evolved into later engines like steam locomotives, which are trains, engines in factories, and this fueled the Industrial Revolution, and even automobiles. So the engineer's quest to build a better engine taught us most of what we know about heat and energy. First, let's learn about steam engines and how they work. I have a picture of a train on the left, and this is a typical steam engine. We're going to talk about the different parts, and I'll try to circle them as I go so you know what we're talking about. So we're going to study how energy flows in a train's engine. So we start in the firebox. And in the firebox, we have coal that's burning. It doesn't have to be coal, but it usually is coal on a train, at least an old school train. And the burning coal makes flames, which heats water to hot steam in the boiler. In the boiler, the heat heats water in the cylinders, and this causes the water to boil. And we know that when things go from liquid to gas, they expand quite a bit, and they can do work. So part of the hot steam's energy is converted to work to power the train. So when the cylinders, which have steam in them, expand and push the piston goes and turns the wheels of the train, doing work. So of course, the water doesn't necessarily cool to room temperature while it's doing work. It will lose a lot of heat, but it won't necessarily be the same temperature as the atmosphere. The rest of the energy is transferred as heat is released from cold steam into the atmosphere as the steam then cools to room temperature. I have a little diagram on the right also of what's happening. We're going to start at the bottom. Coal is going to burn and make hot steam. The hot steam is going to transfer its energy as heat to the steam engine. The cylinders are going to expand from that hot steam. And as the cylinders expand, they're going to push the pistons, which provides the energy as work to turn the wheel. But not all of it goes to work. Some of it gets released as cold steam, and the cold steam transfers its heat into the environment. And that heat transfer there is actually entropy. Once the cold steam becomes the same temperature as the environment, as room temperature, then entropy is maximized, and we're going to talk a lot about that in just a minute. Now we're going to watch a quick video from PBS, and this is just a section of it, but it talks about the two main scientists who developed the steam engines and formulated our understanding of heat and thermodynamics that we still follow today.
Let's start from the beginning. In 1824, Sadi Carnot published his Reflections on the Motive Power of Fire, in which he revealed the theory for perfect engine efficiency. Heat engines, which in Carnot's day were the newfangled steam engines, work by turning the flow of heat energy into mechanical energy. For heat to flow, you need two reservoirs of different temperature. A perfectly efficient engine, one undergoing the Carnot cycle, converts all transferred heat energy into useful work. In principle, that work can then be converted back into heat, and so the temperature differential can be re-established. However, an inefficient engine will slowly deplete the difference in temperature, reducing the heat flow, and the engine winds down. Around a half-century after Carnot, Rudolf Clausius was inspired to quantify this tendency of heat energies to decay over time. Enter entropy. Clausius defined entropy as the internal property that changes as heat energy moves around within a system. Specifically, the change in entropy of each reservoir is the heat energy going into or out of that reservoir divided by its temperature. For a Carnot cycle, the overall change in entropy is zero, but for any less efficient cycle, entropy increases. In fact, an increase in entropy means that the heat reservoirs are approaching the same temperature, reducing their capacity to do useful work. Carnot and Clausius's work revealed entropy as a measure of how evenly spread out a system's energy is. The more evenly spread, the less useful the energy is. And for an isolated system, the best you can hope for is that the separation of energy and the entropy remain constant. In reality, it will almost always increase unless energy comes in from the outside to re-establish the temperature differential. This understanding of entropy is in terms of flowing heat, and it came from the days when many, including Carnot himself, believed that heat was a physical fluid called caloric. It took a revolution to understand the reality of entropy. That revolution was statistical mechanics, founded by the great Ludwig Boltzmann with his kinetic theory of gases. This theory explained thermodynamic behavior as the summed result of the individual motion of tiny particles under Newton's laws of motion.
In the background of the PBS video, I know you saw the cylinder moving up and down, transferring heat from the hot reservoir to the cold reservoir. Here we have a diagram of the same thing happening, and I just kind of want you to follow the diagram, and I'm going to orient you to the diagram of what's happening. In the first step, heat is absorbed by the system in the upper left corner and released to the surroundings in the lower right corner. And in the top half, the gas in the cylinder is expanding and doing work on the surroundings. In the bottom half, the surroundings are doing work, compressing the gas in the cylinder. I want you to note that this actual engine doesn't exist in real life, but it's a model for the most efficient engine that could exist. And this is what many other engines are compared to. There's this really cool toy that I want to get. It's called the Dippy Bird. It's a really retro toy, and it can be thought of as an approximation of the Carnot engine. I have a short video here on how it works.
It's drinking the water! This is the greatest invention in the world! You'll make $1 million!
A Drinking Bird is some thermodynamic machine that seems to go up and down forever. In this video, we'll see how it works, and I'll show a speed up of a live stream that we recently did, showing how a long time a Drinking Bird will run in total. How does a Drinking Bird work? We have this setup, a cup of water, this glass construction with dichloromethane inside, and a cylinder tube. Notice the tube is longer in the bottom than the top, and we have a rotational axis, and then we have a head. That's a pretty nice Drinking Bird, if I have to say myself. Anyways, first you need a hot environment. We'll represent that with red atoms. Next, you need to wet the head. Okay, so now the head is wet. The water will start to evaporate, going from a liquid to a gas. That will cause evaporative cooling. You know this effect after taking a shower. The water evaporates and cools you off. Like this cat. The cat is wet and it contains a gigantic number of water molecules, each molecule with different speeds. The temperature is the average of all these speeds. The water molecules, the ones with the fastest speeds, are the ones that escapes the surface boundary force to evaporate into air. The remaining water molecules has a lower average speed of movement, and then we see a lower temperature. Also, the substance dichloromethane is actually everywhere in the form of gas. The cooling causes this dichloromethane to condense. This means going from gas form to liquid form. Now look at this equation for the ideal gas. It says the pressure times the volume should equal the amount of molecules times the gas constant times the temperature. We just conclude the temperature T is dropping, as well as the number of molecules N. Something on the other side of the equation must change as well, because this is approximative and ideal gas. We know the volume is constant, and so the pressure must drop. We have a pressure difference between the drinking bird's head and the bottom of it. This pressure difference will cause the fluid to rise. Just like I'm showing here with this giant drinking straw and some water, the pressure difference between my mouth and the water just pushes the water up. This will shift the center of mass, and the net torque around the axis will cause the bird to rotate. Actually, just like this seesaw, the sudden change in the mass causes it to rotate over. Now watch the bottom of the drinking bird. It's very smart. As the bird is tipping over, the surface goes under this tube where the dichloromethane is being sucked up in. That causes the dichloromethane to fall back again. And this shifts the balance so the bird will fall back again. I can show this effect with the giant straw again. If I lift up the sucked water just above the water level, everything falls down. This will cause everything to reset. The dichloromethane is falling down, causing the drinking bird to stand again. Now the head is wet again, and it will start the evaporative cooling. This goes on and on and on. But for how long? Well, here's a live stream showing a total run. You probably figured it will run as long as the room is hot and as long the drinking bird can reach the water in the cup. So yeah, you just have to wait for the water to vaporize. It turns out a drinking bird will run for 144 hours. Now I have a question for you. Why can't you use a normal thermometer that works only by expanding a liquid to build a drinking bird? Then it wouldn't need a pressure difference, and therefore we didn't need no water, and it would run forever. Why can't you do that? Comment below. I hope you enjoyed this video. Next time I'll save your life if you're ever in a situation like this, and I'll tell you the actual physics behind it. Consider supporting these physics videos by either subscribing or joining me on Patreon.
In the Dippy Bird, the hot reservoir stays hot as the atmosphere continuously keeps the dichloromethane in the bottom of the Dippy Bird at a warm temperature. And the way the cold reservoir is maintained is that water evaporates from the head. And since evaporation is a cooling process, the head is cold. The work is done when the dichloromethane expands up the tube and tips over the Dippy Bird. As long as the Dippy Bird can drink from the cup and has water to evaporate to keep the cold reservoir cold, then the Dippy Bird will run. But once it cannot drink and water won't evaporate anymore, the cold reservoir doesn't stay cold, and the whole Dippy Bird's the same temperature. And once that happens, it doesn't run anymore and no more work can be done. The theme here is that whenever the steam engine has transferred heat from the hot to the cold reservoirs and they're now the same temperature, the engine no longer runs. This is just like in a train. If the coal is not being burned in the firebox, then the train's steam and cylinders are the same temperature as the atmosphere and no work is being done, we have to maintain a difference between the heat in the firebox and the temperature of the atmosphere where the steam transfers its heat. And what this showed the scientists who studied the heat engines was that when energy is separated between two systems, or between the system and surroundings, it's useful because it can do work as it flows. But once energy spreads out, once everything's the same temperature, it's no longer useful. One way we can think of entropy is energy that is present but not available to do work. This is super key. I hope that you learn this from this chapter. Entropy is energy that's present but not available to do work. Usually, heat from friction is simply increased entropy since it's not used for any work. Let's look at Carnot and Clausius's conclusions summarized succinctly. This is what they learned from studying heat engines. Number 1, work can be converted 100% to heat. Number 2, heat cannot be converted 100% to work in real-world spontaneous processes. Number 3, the waste heat that did not do work only served to increase the entropy of the universe. That is, transferring hot to cold, nothing else. Number 4, the waste heat cannot be recovered to do work without using even more energy. And let me stop right here and explain that, remember, there has to be a separation from a hot to a cold reservoir in our engines. And some of the heat has to be released into the atmosphere, okay, or transferred to the surroundings. But if nothing can be transferred to the surroundings, the engine won't run. And this part that's transferred to the surroundings without doing any work is the waste heat that they're talking about here. So the fifth conclusion, therefore the entropy of the universe is always increasing from spontaneous processes. And the equation is delta S universe equals delta S system plus delta S surroundings, and because it's increasing, that number has to be greater than 0. That energy that's transferred into the cold reservoir is increasing the entropy of the universe. Another way to express the second law of thermodynamics, remember we said we're going to learn a lot of different ways this chapter, is as we use energy, we degrade its usefulness. So another way to think of the first law versus the second law, the first law of thermodynamics states you can't win, you can only break even. Whereas the second law states you can't even break even. What this is saying in the first law is that, energy can't be created or destroyed, it can only be transferred from one form to another. So that's what they're saying. You can't win, you can't create energy. But when you transfer it one form to another, you can only break even. But the second law of thermodynamics says some of the energy when you do work has to go to increase the entropy of the universe. You can't get 100% work out of it. So that's why they're saying you can't break even. The way our brain interprets time is based on the second law. It summarizes what we have seen and experienced, as well as what we think will happen. So when you watched the video of the glass falling and shattering, and then we played it back and rewind, you knew intuitively which direction was the forward playback and which is the rewind. The pieces would not suddenly come back together and shoot up. This is because the pieces of glass are now spread out in space, and there's no energy to bring them back together and lift them back up onto the table. The basis for this is your intuition of the second law. That's why the second law is sometimes called time's arrow. Remember in the last lecture, we proved that hot always flows to cold because more energy levels will be occupied at the colder temperature than the hot temperature because the rungs are closer together on the ladder. The thing is, that proof was that energy flows spontaneously from hot to cold. But refrigerators, air conditioners, and heat pumps work as heat engines in reverse. They take heat from a cold reservoir and move it to a hot reservoir, making the cold colder and the hot hotter. But they don't violate the second law. There's an external source of energy, here the electric motor, that pumps the piston up and down, instead of a gas expanding and doing it on its own. It moves heat flow from the cold to the hot reservoir, making the cold reservoir even colder. This is how heat is pumped out of a refrigerator or a living room to make it colder than the surroundings, i.e. the atmosphere. So let's go over the diagram real quick. On the left is the Carnot engine. This is our heat engine. This is what we looked at when we were talking about the train. And on the bottom, we start with hot steam, and it transferred its energy into the steam engine. The steam expanded, and when it expanded, it moved the pistons, which caused the energy to turn the wheel. And the steam that was cooler, but not the same temperature as the atmosphere, was expelled from the train as colder steam, and it transferred its heat into the atmosphere, and that transfer was entropy. Once the steam is cool and the same temperature as the atmosphere, that energy that went into the atmosphere can't do any more work. It's not useful energy anymore. So let's look at the diagrams on the right, the refrigerator, air conditioner, and heat pump. So again, this is making cold colder and hot hotter, but it's not violating the second law because we're using energy. We're putting in energy from another source. We're plugging it in, and that electrical energy is driving the refrigerator motor or the heat pump. Okay, and so as the motor is working or the heat pump is working, it's moving heat energy. It still is a heat flow, but the heat is flowing from the cold atmosphere in the refrigerator or outdoors on a cold day, and it's moving the heat into the kitchen in the case of the refrigerator, and it's moving the heat into the house in the example of the heat pump. How can we define entropy? Well, last lecture we talked about microstates and Boltzmann's definition, and we said that entropy change was the Boltzmann's constant times the log of the ways that the system's molecules could be arranged in the final state divided by the ways that they could be arranged in the initial state. But when we're working in the lab, we're not like calculating with probability and statistics and thinking about individual atoms and molecules. And that's not what Carnot and Clausius were doing either. They came up with a thermodynamics definition. So I have a couple questions for you. What has the greater impact, shouting in a library or shouting in the school cafeteria? I hope you chose shouting in the library. That makes a huge impact on the silence. But if you shout in the school cafeteria, it's already super loud. Your voice doesn't really add much to the noise level. What about giving $1,000 to a millionaire versus to a poor college student? Well, that $1,000 isn't really going to mean very much to a millionaire, but it's going to mean a ton to a poor college student. So similarly, the same quantity of heat has less impact when it's transferred to a hot environment than to a cold environment. Okay, so if it's already hot and you transfer a little bit of heat, doesn't make that much difference. But if it's cold and you transfer heat, it makes much more difference. The thermodynamic definition of entropy takes into account the impact of a heat transfer that just spreads out energy but does no work. So something like friction. The equation is delta S equals Q over T. Remember that Q is heat flow and capital T is temperature. Note that we're not talking about a change in temperature here. The temperature must be constant. And we'll talk about that a lot more in the next lecture. So let's do a problem. Let's calculate the entropy change when 10 joules of energy is added reversibly to a system at 10 Kelvin. We have our formula, delta S equals Q over T. So here, Q is 10 joules, and the temperature is 10 Kelvin. So delta S, the entropy change, is 1 joule per Kelvin. Now, in B, we're looking at the same 10 joules of energy, but it's being added to something hot, much hotter, at 1,000 Kelvin. So delta S equals Q over T. Again, we have 10 joules, but this time 1,000 Kelvin. So the answer is 0.01 joules per Kelvin. The impact of adding 10 joules is much greater at 10 Kelvin, it's 1 joules per Kelvin, than at 1,000 Kelvin. We can also say that the 10 joules was more diluted at a colder temperature than a higher temperature. Well, have we done what we've set out to do? I hope so. I hope we can describe how engineers, specifically Carnot and Clausius, were studying steam engines, and they helped form our idea of how energy flows. They saw that work was done when heat was moved from a hot reservoir, like the coal burning in the train, and when it was moved to the cold reservoir, like the steam cooling off in the atmosphere. And we know that there has to be a difference between the hot and the cold for the engine to work, and some heat has to just be transferred to the cold reservoir, to the atmosphere, and that waste heat is called entropy. And that is calculated in a macroscopic fashion using the formula delta S equals Q over T, heat flow divided by the temperature it's at. So we're looking at the impact of the heat flowing at a particular temperature. Hopefully all this will become clear as we do some in-class problems. I'll see you at the next lecture.